Today, we are taking on, well, a genuinely complex area of engineering.
Definitely complex. We're talking about the stability of our electrical power grid.
Right. We've been immersed in some pretty dense technical documents, really focused on how power systems move, breathe, and sometimes how they shake quite violently.
It's not just dense, it's absolutely foundational. Our sources focus on a specific vulnerability known as Low Frequency Oscillations, or LFOs.
LFOs.
These are critical oscillations, typically in a frequency range from about zero point 0.1 hertz up to maybe 2.0 hertz.
So quite slow oscillations then.
Relatively slow, yes, but if they aren't properly controlled, well, they can lead to major system collapses. Big trouble.
Okay, so our mission today, for you listening, is to provide a shortcut, maybe, to understanding this complexity. We need to unpack how these LFOs are classified.
Exactly. Because you can't really tackle a dynamic problem effectively until you know precisely what kind of dynamic problem you're facing.
Makes sense. And the sources, they seem to identify three key ways to classify them.
That's right. Three essential approaches.
Yeah.
One based on damping, another based on the origin of the oscillation, and a third based on system dynamic characteristics.
Okay.
But stepping back for just a second, the crucial thing to remember is that the power system is this huge, nonlinear dynamic beast.
Right.
And depending on its initial state, what's happening right then and any input it receives, it can display a really wild variety of responses.
So classification is about trying to impose some order on that potential chaos.
Precisely. We're trying to structure our understanding of that wild behavior.
Okay. Let's start then with the question of, well, causation. Origin-based classification.
Good place to start.
This forces us to ask, is the oscillation inherent to the grid itself, just how it works, or is it being caused by something external, something attacking the system?
And the sources define this fundamental split as natural response versus forced response.
Natural versus forced. Okay,
Okay.
tell us about the natural response first.
The natural response is basically the system reacting to itself. It's characterized only by the system's own inherent ways of oscillating its modes.
So it's directly related to the system's internal dynamics, things like its electromechanical modes.
Exactly, like the famous inter-area oscillation mode. That's a classic natural response.
Oh, okay.
These oscillations exist simply because the power system is inherently nonlinear. These modes are its signature reactions, you could say.
So if I'm getting this right, the frequency, the damping, how quickly it dies down, and even the shape of this natural response are essentially inherited, like from the grid's dynamic DNA.
That's a great way to put it. It's what the system wants to do when it gets nudged or disturbed.
Which means for the system to actually survive day to day, it must have good internal damping. It needs to suppress these natural reactions quickly.
Precisely. Good damping is non-negotiable for stability. And actually, we see this natural response happening all the time, every day.
Oh, really? How so?
It manifests in two main types. First, there's what's called the ambient response.
Ambient response, like background noise.
Exactly like background noise. Think of it as the system's reaction to countless small random changes happening constantly. Tiny load shifts, minor voltage fluctuations. It's the grid just, well, breathing.
That's fascinating. So if it's happening all the time, this sort of low-level chatter, how do grid operators tell the difference between that normal ambient stuff and, say, a real problem that's just starting to emerge?
Yeah, that distinction is absolutely key. It often comes down to the magnitude and looking closely at the frequencies involved, spectral analysis.
Oh, okay.
Ambient responses are statistically small, they look random, and crucially, they're usually heavily positively damped. They die out fast.
Right.
A real developing problem, even one that becomes sustained, typically shows up as a clearer, larger signal at a specific, often worrying frequency. But that constant background noise, that's why monitoring systems need to be so incredibly sensitive and sophisticated.
Got it. So ambient is one type of natural response. What's the second?
The second type is much more dramatic,
Yep.
the transient response.
Transient. Okay, this sounds like it follows a bigger event.
Exactly. This is the immediate reaction right after a sudden large disturbance. We're talking a major fault on a line, a big generator tripping offline unexpectedly, or a significant block of load being dropped.
The big stuff.
The big stuff. And the transient response is actually quite complex because it involves two stability phenomena sort of woven together.
Whoa, what are those?
First, you have the initial transient stability issue. That's the massive slow power swing that happens as the generator's angles try to find a new stable operating point after the disturbance. It's a big adjustment.
Like the system reeling from the initial shock.
Perfectly put.
Yeah.
But immediately following that, As that big power swing starts to settle down, you see the small signal stability phenomenon kick in.
And that is,
That's the system's natural oscillatory modes being excited by the disturbance and then hopefully damping themselves out. It's the smaller oscillation riding on the tail of the big swing.
huh. It's almost like if you hit a large bell really hard. The initial massive dong is the transient stability swing, and the ringing or humming that continues afterwards and fades away, that's the small signal stability part. The natural modes vibrating.
That is excellent analogy, yes. The initial impact and the subsequent ringing.
Okay.
And critically, both parts rely heavily on the system's inherent ability to self-correct, primarily through damping.
Right. Okay, that makes sense for natural responses. Now let's switch gears to the other side of that coin. The forced response.
Yes, the forced response. This is critical because it often represents, as you said earlier, an attack on the grid's dynamics from outside or from within due to malfunction.
So not the system's natural reaction, but something making it oscillate.
Exactly. It's a system response directly associated with an external input, or often some piece of equipment that's malfunctioning rhythmically.
The sources gave some pretty clear examples here, didn't they?
They did. A classic one was a malfunctioning steam valve on an old-school generator. If it starts cycling open and closed, it injects this rhythmic disturbance into the power balance.
Okay, that makes sense.
Or, perhaps more relevant for the modern grid, you might have nonlinear industrial loads, like big arc furnaces.
Right, I've heard those can cause issues.
They definitely can. Or, increasingly, you might see issues with inverter-based resources, solar farms, wind farms, battery storage. If their control systems aren't interacting correctly with the existing grid impedance, they can inadvertently inject oscillations.
So the forcing function is this external rhythmic disturbance.
Precisely. And here's a key complication. That input signal, that forcing function, it's almost never a clean, perfect sine wave at a single frequency.
Why is that?
Well, things like cycling valves or arc furnaces, they create complex waveforms. And because the power system itself is nonlinear.
Ah, the nonlinearity again.
Always. It means the system's response often includes multiple frequencies. You'll see harmonics, multiples of the fundamental frequency of that forcing signal.
Which must make it harder to pinpoint the source sometimes.
Much harder, yes.
Yeah.
The signal gets messy.
Okay, so you have this forced oscillation being pushed onto the grid. Is the main danger just the fact that it's there, messing things up? Or is it about how it interacts with the grid's own natural tendencies?
It's definitely the interaction that keeps system operators and engineers awake at night. The sources are very clear on this. The terrifying risk is resonance.
Resonance. Okay, physics class flashbacks. Bad news.
Very bad news. If that external forcing function happens to inject energy at a frequency that is very close to one of the system's own natural modes,
Uh-oh.
and particularly if that natural mode is already poorly damped, you hit resonance.
And resonance means things get amplified, hugely amplified.
Catastrophically amplified. You're essentially pushing the swing at just the right moment in its cycle, adding more and more energy. The oscillation rapidly grows to dangerously high amplitudes.
Way beyond what the system's controls were designed to handle.
Way beyond. And remember, as our grid evolves, we're adding more devices that can create these kinds of forcing functions. Things like HVDC transmission lines, large banks of power electronics for renewables.
So the potential for these forced oscillations and potentially resonance is actually increasing.
It's certainly a growing area of concern and research, yes. The interaction between these new technologies and the grid's inherent dynamics needs very careful management.
Okay, wow. That risk of resonance, that threat assessment, it leads us perfectly into the second main classification framework. Classification by damping.
Exactly. We've talked about what caused the oscillation, natural or forced. Now we need to ask how stable the system is when facing it. How well is it handling the oscillation?
And this is all about the system's oscillatory stability, right? How well it damps things down.
Precisely. Damping is fundamentally about how quickly the system dissipates the energy tied up in that oscillation. We measure it using the damping ratio, often represented by the Greek letter zeta.
Zeta, okay.
Think of your car's shock absorbers. Good shocks mean good damping. You hit a bump, the car settles quickly. Bad shocks, poor damping, and the car keeps bouncing. Same idea in the power grid.
Got it. And the sources break this down into 3 clear categories based on that zeta value.
Yes. Positive damping, which is kudruk greater than 0. Zero damping, where ok equals 0. And negative damping, where pruk is less than 0.
All right, let's start with a good one. Positive damping. This is normal.
Positive damping is normal. It's healthy. This is what happens with most routine events. A small fault clears quickly. A minor load changes.
A system just handles it.
The system handles it. Its inherent characteristics and control systems provide enough positive damping, meaning energy is removed from the oscillation, so the amplitude shrinks, usually quite quickly.
Like that well-damped bell fizzling out fast.
Exactly. The oscillation typically dies out within a few seconds, maybe tens of seconds, and the system returns to a stable state. It's a temporary event.
Okay, easy enough. Then we get into the problem zone with zero damping, also called sustained or undamped oscillations.
Yes, now we're talking trouble. These are oscillations that, once they appear on the system, they just sustain themselves. They don't grow, but critically, they don't go away either without some kind of corrective action.
They just keep going at a steady amplitude.
That's the defining feature. They maintain their amplitude indefinitely. Now, the initial trigger might have been something routine, a normal disturbance.
If the system fails to damp it out.
Right. The failure to dissipate the energy, the sustained nature, is often linked to something like a controller malfunctioning slightly, or maybe a feedback loop in the system that's become marginally stable. It's stuck in this oscillating state.
So it's like the system found a frequency it can oscillate at without losing or gaining energy.
Precisely. It's stable, but stable in an oscillating mode, which is not where you want it to be. It's a major warning sign.
But hang on, if they're just sustaining and not growing, why are they so dangerous? They haven't actually crashed the system yet, right?
That's a really important question.
Yeah.
They are dangerous for a couple of key reasons. First, they drastically reduce the system's operating margin.
How so?
Think of it like this. The grid needs some breathing room, some reserve capacity to handle the next disturbance. A sustained oscillation essentially uses up that dynamic margin. It's already stressed.
Okay. So it's vulnerable.
Extremely vulnerable. The moment a second event hits, even a smaller one, while the system is already dealing with that sustained oscillation,
It could push it over the edge.
it very easily could. That sustained mode can quickly transition into the truly catastrophic category, negative damping. Plus, sustained oscillations can mask underlying weaknesses or other potential problems. There's serious red flag.
Okay, that makes sense. Which brings us to the worst case scenario. Negative damping, zeta less than 0.
This is the most dangerous classification, absolutely, because negative damping means the system isn't removing energy from the oscillation, it's actually adding energy to
It's
it.
feeding the oscillation.
It's feeding it, making it grow.
Yeah.
When an oscillation is negatively damped, its amplitude gradually increases over time.
So it might not look too bad initially.
Exactly. It might start off looking like a normal, positively damped oscillation that should be dying out, or maybe like a sustained one. But subtly, over seconds or perhaps minutes, it starts growing.
Exponentially.
Often exponentially, yes. It grows and grows in size until it reaches an amplitude the power system simply cannot withstand.
And then what happens? Protective relays trip.
That's typically the failure mechanism. Protective relays see the huge swings in voltage or current and operate to protect equipment, tripping transmission lines or generators,
Which can then lead to cascading failures.
leading potentially to widespread outages, even blackouts. This is the slow-motion catastrophe scenario.
Wow. So it sounds like the biggest vulnerability here isn't necessarily the thing that started the oscillation,
Often not, no.
but rather the state of the grid and its control systems at that moment, the thing that determines whether the damping is positive, 0, or negative.
You've hit the nail on the head. The transition from a harmless, quickly dying oscillation to a catastrophic, growing one can hinge entirely on the system's operating point, the tuning of its controllers, that very thin margin between stability and instability.
That's a sobering thought. Okay, we've covered origin and damping. Now we need that third layer the sources mentioned, classification by system dynamic characteristics.
Right. This layer is often crucial for figuring out how to fix the problem once you know its origin and damping status.
So this is about where the oscillation is happening and what parts of the system are involved.
Exactly. It categorizes oscillations based on the physical location and the relative movement of the generators involved. Who is swinging against whom?
And knowing that tells you where to apply the fix.
It points you towards the right mitigation strategy. The sources generally identify 3 major types of these characteristic modes.
Okay, let's start with the faster, more localized ones.
Those would be the local modes. As the name suggests, these typically involve just a single generating unit or maybe a small group of generators at the same plant swinging against the rest of the power system.
Okay, like one machine oscillating relative to its neighbors.
Pretty much. You can often visualize it as swinging against the local substation or the immediate connection point, the bus bar. They tend to be faster, maybe in the 1 to 2 hertz range.
And because they're local.
Because they're local, the solution is usually local too. They're often effectively managed by controllers installed right on that specific generator, particularly devices called power system stabilizers, or PSS.
PSS. Got it. Local problem, local solution. Makes sense.
Mostly, yes. Then we move up in scale to the wide area threat, the inter-area modes.
Right. These sound like the big ones, the ones that make the news when things go wrong.
They often are, yes. Inter-area modes are slower, typically operating down in the 0.1 to 1.0 hertz range.
Much slower.
Much slower. And what defines them is that they involve large, geographically distant groups of generators swinging against other large groups of generators, usually across a major transmission corridor that connects them.
So like you said earlier, maybe the whole eastern seaboard swinging against the Midwest.
That's exactly the kind of scenario, because they involve such huge parts of the system and span such long distances.
Local controls aren't enough.
Local controls, like a PSS on one generator, have very little effect on these massive slow swings. Their low frequency and wide geographical spread make them incredibly difficult to damp out using only local measures.
So what do?
You generally need coordinated wide area control schemes, things that can look at the bigger picture and coordinate actions across different regions or different major generators. It's a much bigger control challenge.
Okay, so if an operator sees, say, a negatively damped oscillation shaking the system at 0.5 hertz.
Ding, 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 ding. That low frequency immediately flags it as almost certainly an inter-area mode problem.
And that tells them they need to think bigger than just adjusting one machine. They need a regional coordinated response.
Precisely. The characteristic mode instantly tells you the scale and likely location of the problem you're fighting. It guides the entire mitigation effort.
Fascinating. Okay, local modes, inter-area modes. Was there a third one?
Yes. The sources also discuss torsional modes. These are a bit different because they are fundamentally mechanical issues within the generator itself.
Mechanical, so not the whole generator swinging against the grid, but something inside the machine.
Exactly. It's the different parts of the long turbine generator shaft, the turbine sections, the generator rotor twisting and untwisting against each other, like wringing out a towel.
Wow. And what causes that twisting?
It's usually excited by electrical events on the grid, particularly things like subsynchronous resonance or interactions with certain types of power electronics or series capacitors. But the oscillation itself is the physical shaft flexing.
That sounds damaging.
Extremely damaging. These are very high-frequency oscillations, often 10 hertz or even much higher, and they can cause severe fatigue damage to the multi-million-dollar shaft system very quickly.
So torsional modes are less about immediate grid-wide stability?
And more about protecting that specific, expensive piece of rotating machinery from mechanical failure. Still critical, but a different kind of problem than inter-area instability.
Okay, that really ties the three classification methods together then. Origin, damping, and characteristic.
It gives you the complete toolkit, really. First, you understand the origin. Was it natural or forced? That helps you find the root cause, the source of the energy injection.
Right.
Then you assess the damping. Is it positive, zero, or negative? That tells you the immediate threat level. How urgent is this? Is the system stable, marginal, or actively unstable?
Okay.
And finally, you identify the dynamic characteristic. Is it local, inter-area, or torsional? That tells you where the problem is manifesting physically and guides how you deploy the solution.
So you might have, say, a forced oscillation from a malfunctioning controller.
That happens to excite a naturally occurring inter-area mode.
And because the system conditions are just wrong, that mode becomes negatively damped.
Exactly. That's the kind of chain of events these classifications help you diagnose and hopefully interrupt.
Fantastic. So with that synthesis, hopefully you, the listener, now have the fundamental language you need to really assess the stability risks that come with these low-frequency oscillations.
Yeah, moving beyond just knowing the term LFO to actually grasping the different facets, where it came from, how dangerous it is right now, and what part of the system is actually moving.
You can start to distinguish between the grid's inherent background hum and maybe a more directed external dynamic attack, and then judge the immediate threat level of either one.
And we noticed something quite important, I think, that the really dangerous situations, sustained zero damping, and especially the growing negative damping oscillations, often point back to vulnerabilities in the grid's control systems.
Right, either a controller malfunctioning or an unexpected resonance effect happening.
Exactly, which raises a really interesting question to perhaps leave you with, considering how absolutely critical damping and control are for system survival, especially as we integrate more complex, fast-acting power electronics from renewables and storage? Should the main focus of grid engineering perhaps start shifting? Maybe less emphasis purely on adding massive traditional sources of inertia, like big spinning generators,
And more
and
towards
more towards developing really sophisticated, maybe even AI-driven adaptive control systems. Systems designed to instantly detect these subtle dynamic threats, classify them using the frameworks we've discussed, and automatically take corrective action before they can escalate.
self-healing controls almost.
Something like that. It's definitely something to ponder as our power grid continues its massive, rapid evolution. How do we best manage these increasingly complex dynamics?